Hello, welcome to the physics seminar, part of our spring physics seminar series of talks. Today we have Michael Kavlin, and Greg Pawlowski is going to introduce him.
Yep.
So, Greg, please.
Yeah, I was going to introduce Michael. He's from my home institution of the University of Minnesota. Michael's a relatively new faculty member, assistant professor. I think officially you started January of last year, right? So must have been very surreal to start and then a pandemic happened. So it's very non-traditional beginning, I guess. But he's part of our Minnesota Institute for Astrophysics, and he does work in multi-messenger physics. So looks at gravitational waves and electromagnetic data, so optical data. Okay, so you must have a new hire too then at that time. So so Michael's previously worked on LIGO, and I still working on LIGO, and is also proposed to work on the LISA. And I guess maybe I should mention, well, he might talk about it here in his talk, but LIGO, if you're not aware, is the gravitational wave experiment that is terrestrial based, uses interferometers, while LISA is proposed to be space-based, to actually go in space and do this. And so I think also Michael's part of our program at the University of Minnesota, where we've introduced a minor degree for graduate students to study data science and multi-messenger astrophysics. And so with that, I guess I'll let Michael take over.
Thanks for that really nice introduction. Yeah, it was weird. I showed up, I started teaching, in person, and then suddenly weren't in person anymore. But I think that gave me a little bit of an advantage somehow, because I wasn't the only confused one anymore, right? Everyone was confused how to teach online. So I was, the same as everyone. But anyways, yes, so I'm Michael. I'm an assistant professor here at in MIFA. And I won't actually be talking about LISA today. I decided it would just be too much to try to cram into one talk. I'll be talking about LIGO and their gravitational counterparts, and I titled my talk kind of the obnoxious, a technical ecosystem to enable multi-messenger astrophysics, and I'll try to explain what I mean as I go here. So to kind of set the stage, I think I don't have to make too hard of a case that we are in a golden age for astrophysics. So I put 4 experiments down here. Many of them are pretty famous at this point. We have Farrer-Rubin Observatory, or LSST, which is going to be a 8-meter class optical wide field telescope that's sort of, nominally going to change optical and near-infrared astronomy for the next decade once it comes online in a couple of years. TESS is a planet finder up in space doing wide field continuous cadence observations of identifying exoplanets. We already mentioned LIGO and Virgo, which are LIGO is a pair of large 4-kilometer scale interferometers in Hanford, Washington, and Livingston, Louisiana, and then Virgo is a 3-kilometer scale interferometer in Pisa, Italy, and it's part of a actually growing global network of ground-based interferometers detecting gravitational waves from compact binaries and other things. I noted IceCube down here, which is doing neutrinos, and of course, given the crowd that I'm talking to, I should also mention DUNE, which is another neutrino experiment. And so, in the next, 10 years, there will be, truly, groundbreaking experiments in various areas and sort of, covering from gravitational waves to neutrinos to optical astronomy. And so we're really in an exciting time to be in this field. And so I'll start out by talking I'm sure most people have heard of LIGO and what's been up, but I won't harp on this for too long. But I'll start out with, 6 years ago now or so, with the first binary black hole detection by LIGO. And so what you're seeing in this plot, can you see my can you see my cursor, by the way, just to check? Is that working?
Yep, I can see your cursor.
Great,
Yeah,
great cursor. Okay, so this is the gravitational wave strain, and so these interferometers are measuring relative displacements in space-time, and the strain is basically the displacement over the length of our interferometer cavity. So in this case, 4 kilometers. And so these numbers we're talking about are very, very small. And so this is what we now identify as the merger of 2 moderate mass binary black holes. And so this is so you have this characteristic chirp as you have these 2 black holes going around each other, and they go whoop as they go and merge. And so this is the signal that we measured in both Hanford, Washington and Livingston, Louisiana. So in both of our detectors. And you can see overlaid here, the plot from numerical relativity, where we take Einstein's equations and we actually simulate those. And so this was, groundbreaking for many reasons, but in general, there was great excitement to confirm that indeed binary black hole mergers exist, and that general relativity was correct. And so since 1509-14, we are up to something like a bit less than 50 confirmed, at least outwardly confirmed, binary black hole mergers. And so that was in what's known as the LIGO and Virgo's first observing run. We are now past our 3rd observing run, with the expectation to start the 4th observing run sometime in 2022. And so this has been an unmoderated success, especially with regards to our, the program searching for binary black holes. But I'm here today talking about multi-messenger astronomy, and so I'm predominantly interested in objects that not only can you detect in gravitational waves, but you can also detect at other wavelengths. And so as you can imagine, in the case of binary black hole system, most are formed out in the field. And so you don't expect to actually have that much necessarily matter accreting around them, gas, such that if anything, you'd expect a very, very weak optical signature, for example. Now, as a counterpoint, we have detections of binary neutron stars. And so, so in this case, instead of 2 black holes, you have 2 neutron stars that merge. And so during our 2nd observing run, we had this very exciting signal, and nowadays it's 170817 back in August of 2017. And so this object was first detected by LIGO and Virgo. And so in general, the way that you can kind of tell is, so binary black hole mergers last of order, tens of milliseconds, hundreds of milliseconds, something like that in our band. Whereas as you go to lower and lower mass, they last, tens of seconds to minutes in our band. And so we had this very low mass merger detection. Even more exciting, shortly thereafter, we had a detection by the Fermi gamma ray burst monitor instrument up in space. And so this was the first coincident detection between gravitational waves and gamma rays. And so this indicated that it was something special. And so if you look over here, so this was the sky localization in pink here from the gamma ray burst monitor. And eventually when, since all 3 detectors were on, we had really highly well localized signal, and that's in green here. And after quite a comprehensive search, optical astronomers identified the actual location of the counterpart. And so we were able to go down from the gamma rays covering hundreds of square degrees on the sky, the gravitational wave signal down to order 40 square degrees on the sky. And then by searching through galaxies in the localization, we found the optical counterpart to this system. And so this set off I would say, one of the most comprehensive follow-up endeavors in history. It was detected not only in gravitational rays and gamma rays in the optical, but subsequently in the radio, the X-ray, the UV, et cetera. And so it's one of the best studied objects in history at this point. And so this is a nice little video, hopefully it plays, of this is the galaxy originally, and then here's the counterpart as time goes on. As you can see on the x-axis here, we're going from only in the course of a week, you go from this bright blue object to something that's rapidly reddening and peaking in the near infrared to the infrared after less than 2 weeks. And so, so that's all well and great. So we detected the counterpart to a binary neutron star, but what exactly do we expect to see from, what exactly does this mean, right? And so to explain that, we'll sort of break down the compact binary coalescences a little bit here. And so these are, this is an artist's rendition of what, some of the components that go in when you have a merger of 2 neutron stars or a neutron star black hole. And we'll break these down individually. And so to start with, when we talk about this gamma ray burst, so what is it? So you have this collimated jet that is, so you have some central engine and you have a collimated jet that perhaps interacts with what we call a cocoon, but basically there's some amount of material that's being ejected in this merger, and this collimated jet comes and breaks out of this cocoon, producing this prompt emission in gamma rays. And so this is what the gamma ray satellites see. Traditionally then, as this jet moves outwards, it interacts with the interstellar medium and creates this panchromatic afterglow that lasts hundreds of days, very, very long time. The part that we'll be focusing more on here is known as a kilonova, and we'll get to the physics of that in a second. But nowadays, after a lot of analysis of 17817, people agree that in general, there's at least two components. One is known as the tidal ejecta, or basically the part where you have the binary neutron star going around each other. Material rips off due to tidal forces and sort of is ejected that way. We have another component that's known as a wind, or basically the sort of movement in the material that forms an accretion disk around the remaining object, either the neutron star or the black hole after coalescence. And so, so what are these kilonovae? And so to quote, I'd say the most famous theorist in our field, electromagnetic counterparts of compact object mergers powered by the radioactive decay of our process nuclei. And so what does that mean, right? So the vision here is if you start out with your proton and neutrons in some kind of seed nucleus, we have an environment like in a neutron star merger where you have a great excess of neutrons, right? And so these neutron star mergers are great for that. There's a lot of free neutrons floating around, and due to the fact that they're moving at very, very, very high velocities, some fraction of the speed of light, they are able to overcome forces such that they can come together and glom onto these seed nuclei. So unsurprisingly, these are unstable because now we have this great excess of neutrons, on this seed nuclei, and so they undergo radioactive decay and are producing gamma rays at that point. And then because the material that is surrounding there, so you have this, all this neutron matter, right there, these gamma rays thermalize into, some fraction of them thermalize into this dense ejected material. And so you have gamma rays that some are, escaping, but some of them are running into these, into the seed nuclei, and they're heating it up. And so it's this thermalization from the gamma rays that is heating up the surrounding ejecta and sets the temperature for the system and from simulations, we get something like 10,000 Kelvin at a day or something like that. And so this 10,000 Kelvin signal is then, of course, thermally emitted at relatively long wavelengths in the optical near infrared. And so this is what we see with this kilonova emission. This is what we're talking about when we say this what a kilonova is. This is this thermal emission from this thermalized material from these R process nuclei. Okay, and so so that's all well and good. So we've with this one event, we've confirmed a few things. One, that short gamma ray bursts are actually due to compact binary coalescences, or at least some fraction of them are, so that's really good. We have been able to confirm that at least some fraction of our process nucleosynthesis, which leads to heavy element formation, it's responsible due to these compact binary mergers, and we have this really, really well studied event. But there do remain plenty of questions even after our sort of golden event that we had a few years ago. So for example, it's still confusing why 170817 was so bright and so blue early. And so for you'll think to yourself, well, if I have something that's thermalized and should be emitting in the near infrared, why was it so hot, basically? And is this blue emission that we saw ubiquitous in all of these neutron star mergers? Due to observational effects, there was a 10-hour gap between when LIGO saw the signal and we were able to identify the counterpart. The night hadn't risen yet in Chile, which is where the telescopes were that eventually observed the signal by the time that at the time that we detected 170817. And so we didn't actually see this object for the first 10 hours. And so we don't have any sort of understanding really of what the evolution of the emission was over that time. For example, how bright was it at the beginning? Was there some sort of rise? Did it start as a peak, and has it been falling since? More science questions, let's say, do all of these neutron star mergers generate this relativistic ejecta that undergo our process nucleosynthesis to make heavy elements? We don't know. This one clearly did, but we'll talk about the next observing run in a few minutes, and we did not see any. We have not seen any kilonovae since, and so it seems plausible that only some fraction of these actually do. And then finally, and it'll take more mergers to answer this question, but can compact binary mergers on their own reproduce the heavy element abundance that we see in the solar system? So there's a paper from a couple years ago now where it was posited that perhaps stellar collapse could have conditions that could generate our process nucleosynthesis in a similar way to these kilonovae. And so is that a channel that is important, or are compact binary mergers really the only game in town? So there's a lot of science that was done with 170817, and we'll talk about some of what we've been up to with it since. There's a lot of work to be done that can't be answered with one event, and so we're very interested in finding more of them. Okay, so that was during the second observing run. That was back in August of 2017, and we've been busy since then. And so this is my kind of schematic of what happened during LIGO's third observing run, which happened over the last few years. And so the events that I'll highlight here, so 0425, we had our second confirmed binary neutron star event. It was higher mass than the 170817 event. There was no confirmed optical counterpart for that event. And we posit that might be due to its relatively high mass, and therefore it was less likely to produce ejecta that was appropriate to find with optical telescopes. But again, we need more of these to confirm that to be true. We had our first high significance neutron star black hole candidate. When we put out when LIGO and Virgo put out the paper, we deemed that, so this event was cool for a few reasons. So one, it was our first confirmed merger that had a high mass component and a low mass component. And where by low mass component, I mean something right around 2.5 solar masses or so. And so further analysis has probably indicated that that's a binary black hole. So it's probably not our first neutron star black hole candidate, but it was our first object that at least was close. We had a lot of binary black hole mergers, very large. We had a couple of binary neutron star mergers, relatively small. And this was our first pairing of, clearly one from one class and one from, the other class. So we also had two further neutron star black hole candidates that have come out since, and these will hopefully be published in the next few months. But in general, these were exceptional because while this 0814 event had a very high mass ratio, and that is not particularly conducive to getting ejecta material because the neutron star just falls into the black hole. For these events, the mass ratio is more moderate, and therefore they were particularly, let's say, plausible to search for counterparts. And so this is some observational stuff, and I think we'll pass for time. Okay, and so so this is sort of where things stood as of a handful of months ago when LIGO turned off now. But I think one thing that's worth highlighting here is that while LIGO's been making, LIGO and Virgo have been making some moderate number of detections. We're at a couple of binary neutron stars, perhaps a few neutron star black holes, and many binary black holes. We're not too far from a situation where we're going to be expecting, hundreds of binary neutron stars per year. We're going to, right now we're at a couple per year, and we'll be in a situation where we'll be inundated with detections of this kind. And so this is the first point I wanted to make. While the observing and the ability to search for counterparts right now is predominantly, I would say, almost a classical astronomy exercise where LIGO sends an alert. I, with my telescope, go point at the sky map that they produce and go try to find the counterpart individually for each event. In not so long, we'll have an event per day or something like that. And this sort of method will, we will rapidly be, let's say, overwhelmed by the events we have. And so continuing to build up our observational tools, both in terms of the instruments and our technical capabilities, is essential in order to maximize the science that we're doing with these. Okay, and so onto what I'm calling this multi-messenger ecosystem, which, as I said, is a little obnoxious, but we'll sort of touch on various pieces of this. And so as you can imagine that, it's not enough to detect these, you also need to be creating models for the kilonovae and the gamma ray bursts and the gravitational waves in self-consistent ways, such that you are able to analyze the observations that you have, things like Bayesian inference frameworks, and we'll talk just for a second about that, machine learning to efficiently classify the objects that you have, and at the end to do, in this case, cosmology and nuclear physics. So these are two of the areas we'll highlight in this talk, but it's just two of the science cases one can make for these kind of systems. And then at the end, we'll come back and talk a little bit about the instrumentation we're building to try to make all of this easier. Okay, so I'm not going to harp on any of these topics for too long, and I'm happy to come back at the end of the talk for those who like. But the basic idea here is, so you have our process nucleosynthesis, and so what we're doing to simulate the observations we see, we can take measured opacities for various elements and produce opacity as a function of wavelength, and use those in combination with radiative transport to produce light curves, basically. And so for the non-astronomers in the crowd, the way that most astronomers represent optical data is through magnitudes. And so going from U band here, which is in the UV, to G, R, and I, which is predominantly in the optical, out to Z, Y, G, H, K, which is sort of further and further into the near infrared. And so the magnitudes on this axis, it's a logarithmic axis with a confusing 0 point. But the important part here is we have data points in each of our photometric bands going from the blue to the red. And so these are indicated in the points here, and these are directly from 17.17. And what I've done here is I've overlaid in orange the simulation from the radiative transport that relies on these line opacities. And in general, the fit's pretty good. You know, I think I would say one of the big successes of this whole kilonova process was in the theory that came from before it actually predicted what we should see quite well. And so this has been really borne out through 17.17 and has been part of what we've been relying on to make efficient searches for future ones. On the sort of more gravitational wave side, so I mentioned at the very beginning with 150914, one of the great successes there was that we've had these numerical relativity simulations where we take Einstein's equations, put them on computers, and solve for, in that case, the gravitational waves that you expect from a binary black hole system. But what's kind of cool is that you know, a lot of these numerical relativists are also simulating binary neutron star mergers or neutron star black hole mergers. And so in addition to the gravitational waves that you get from the simulations, which is kind of mostly the goal for them, as a byproduct, you also get information about basically what happened to the neutron star material when it was highly disrupted or formed an accretion disk. And so you can use these simulations to make predictions about the amount of ejecta matter you have for a particular binary neutron star, in the cases their masses, and the equation of state for those neutron stars. We'll talk about what equation of state is in a second. But the idea here is we can use numerical relativity to tie let's say the parameters that we care about, how big is the neutron star, how tidally deformable it is, to the amount of ejecta material that I expect to see with my telescopes. So I can therefore go from telescope observations back to, you know, how big the neutron stars are, what their equation of state are, by using the results from numerical relativity. And that's what we've been doing. Okay, so that's a really rapid glimpse into some of the astrophysical modeling that goes into this stuff. And we'll briefly touch on some of the, let's say, the technical framework that goes into using them. And so, unsurprisingly, while, as I kind of mentioned, LIGO's been off for a little while now and won't be back on till at least mid-2022. And so we've since then been developing a relatively robust framework to go from optical survey data to kilonova detections. And so here I will talk a little bit more about ZTF in a bit. ZTF is a optical survey that we use to search for gravitational wave counterparts, but while LIGO's off, it also is just a survey where it takes images of the night sky a couple times a night. And so we've been using this Wiki-Transient facility to search for new potential kilonovae, even without gravitational waves. But the key has been to build an automated framework to go from telescope information, i.e. Information about up to 100,000 to 1 million transients per night, to identify the handful that are potentially consistent with the kilonova signals we're interested in. We're not interested in the core collapse of a star, i.e. what is a supernova. We're really interested in these kilonova signals. And I'll explain in a few slides why they're observationally difficult and or remarkable. But for us, the key has been to build infrastructure to go from this data product at the beginning, all the way through automated telescope follow-up of the interesting candidates at the end. And so this infrastructure that we've been building has been actually remarkably useful even while LIGO's been off. And so I mentioned at the beginning of the talk that the Fermi gamma ray burst monitor saw the gamma rays from Summit 2017. We can use the Fermi gamma ray burst monitor as a source of potential signals for kilonovae for this reason. And so this is an example of an object that we followed up some handful of months ago now. So this is the GRB time. And so I'll highlight the axis here. So we go from the time of the GRB, 0 days here, and then it spans, a couple of weeks, something like this. The first detection by ZTF was within something like 12 hours. And so these are these red and green points here. And our identification of the transient being interesting was at the second night of observation. So kind of a day and a half after the GRB. So in general, we need at least 2 nights. We typically need a couple of nights to identify that these objects are interesting, because kilonovae fade very quickly. And so we're really interested in objects that are quickly fading. And so we're able to identify after even just a few nights, yes, we have a transient here that's interesting. So right at this point is where our pipeline, indicated, yes, we have something we're interested in. And it was only a few hours later that the VLT, which is it's the European large aperture, set of telescopes, and in this case, a large spectrograph, got a spectrum of this object and indeed confirmed it was a GRB at some redshift. And so it's this kind of automated infrastructure. All of this was automated. The cross match between the sort of the observations of the gamma ray burst error circle, all the way through identifying the interesting candidate here. And at this point, we put out the information to the community to get the spectrum. And so, all of this is happening within 36 hours or so of this GRB. And so you can imagine time is clearly of the essence. And so, the technical infrastructure here really determines the kind of science that you can do. So I'm just going to highlight one more object that we were excited about, and sort of as part of this search. We had another different event from the gamma ray burst monitor, which was at least initially expected to be a short gamma ray burst. And so this is an example. These squares here are the tiles of the images that we took, and in green here we have the sets of transients we found. And so even in this 100-degree localization or so, we still had order a dozen potential candidates for the counterpart for this particular gamma ray burst. And so it's not as simple as we point and we identify the thing. We actually have a number of objects that we need to then parse through to determine which one is potentially interesting and which one is the potential short gamma ray burst counterpart. So fortunately, SWIFT is a satellite that has both a UV imager and an X-ray telescope on it, and so it also identified one of our candidates as fading quickly, and therefore consistent with what we expect from one of these afterglows. But what was kind of cool about this one was that 2 weeks later. So this was the observation by ZTF and how we identified it again. So you'll notice that in this case we are observing within an hour or so or something like this, and then the next night we also identified that it was fading quickly. But if you look down here, so that was sort of 24 hours, so sort of technical infrastructure that's good. But out here we have detections by a large aperture telescope after 30 days or so. And so the reason that this is interesting is because the one way to tell the difference between a compact binary merger, i.e. a short gamma ray burst, and the core collapse of some star, which are at least thought to produce long gamma ray bursts, they're often accompanied by supernovae later, right? Core collapse of a star, supernova, right? And so, but you'll notice that this is the fit to just some kind of afterglow model here, in green, red, and orange. And so in order to identify, or at least confirm, that the excess that we identified with this large aperture telescope after 30 days was indeed, the supernova from this long gamma ray burst, it did require, a fully Bayesian framework to fit an afterglow plus a supernova versus just having an afterglow to do sort of all the Bayes stuff correctly. Long story short, we at least believe we confirmed that this this excess was due to a supernova. And that's interesting because it would make it potentially the shortest long gamma ray burst that has ever been found. And by long gamma ray burst here, I mean core collapse of a star, which might have some interesting implications for stellar collapse in general. So I mentioned briefly this Bayesian joint inference work. And so the idea here is it's not enough to just to take the optical data. We have gravitational waves, we have gamma rays, we have optical. And so we can build joint inference pipelines that take not only information from one, but also from the other to jointly constrain parameters. And so I think I like this plot. So this is an example of jointly analyzing 170817 using the gamma rays, the gravitational waves, and the optical data. You get constraints in the same plot on not only ejector parameters, and so this is basically a measurement of how much ejecta you have in terms of solar masses. You get out information on the equation of state of neutron stars, where it's tidal deformability, again, which we'll talk about in a second. And you also can constrain the inclination and the distance of this object, which will be important for constraining cosmology, or H0. And so by building these pipelines, we're able to simultaneously constrain all of these, let's say, really important physics or astrophysical quantities. Okay, so to just touch on the nuclear physics and cosmology here briefly. Okay, so in the neutron star equation of state, the idea here is neutron stars are described by a pressure density relation, and there's numerous models proposed in the literature. Usually they're shown as sort of mass of the neutron star versus its radius. And so the idea is how stiff the neutron star is determines how much it deforms under gravity. And so these tidal effects appear not only in the gravitational waves, which changes the phasing of the gravitational wave form, so you can measure the equation of state in the gravitational waves, but you also get information on the equation of state because it partially determines how much ejecta you might expect, i.e., if I have a kind of a soft neutron star, and so a lot of material, a lot of material to get thrown off to make a brighter counterpart. And so I get information on the equation of state, not only through the gravitational waves, but also in the optical signature. And so we recently went through an analysis where we started with 5,000 equation of states that were consistent with nuclear theory. So we started with these 5,000 equation of states. So all of these little blue lines here are different equation of state. We first passed this set of equation states through constraints from NICER, which is doing X-ray observations of pulsars. And so they have a really cool measurement where they have a simultaneous measurement of the mass and radius of a pulsar, which indeed is great for constraining neutron star equation of states. And so it's one of the, let's say, one of the best ways to rule out equation of states. So you can see going from here to here, lots of blue to less blue. So NICER does a really nice job here. And then once you include from gravitational waves from 170817, again, we have fewer blue lines. And then finally, when you include the optical counterpart, again, fewer blue lines. And so each of these steps in the process, going from including the NICER measurement to including the gravitational waves to including the optical counterpart, each of these improves your measurement of the equation of state, or equivalently, this is a plot of the radius of a 1.4 solar mass neutron star. Further and further constrains the equation of state that way. And so this is the kind of science that you can do by looking at, let's say, one object in many different ways. The other thing I'll just briefly mention is cosmology. And so this is interesting as a field because, as I'm sure many of you are well aware, there's currently a tension in cosmology between measurements from type 1a supernovae and the CMB. And so gravitational waves have been posed as one of the, a potential way to help mitigate this tension, or at least weigh in on it. And so the way this works is that as long as you assume general relativity is correct, from the gravitational waves, you get a distance measurement, and then from the potential optical counterpart, you can get a redshift. And so you have a distance, you have a redshift, you can do cosmology. And so I would say the big issue with this is that in gravitational wave land, there's a big degeneracy between the inclination angle of the binary, basically what angle am I viewing this thing at, and the distance. And so this is the main, let's say the main statistical error that we end up with in gravitational waves. And so if you can find, for example, ways to improve the inclination measurement, such as using electromagnetic observations, you can improve measurements of the Hubble constant. And so in our particular case, so for example, there are measurements using the superluminal motion, or the apparent superluminal motion of the counterpart of 170817, which provides a very strong constraint on the inclination. We also get some inclination information directly from the Kilonovae itself. And so when you include these, you can improve the H0 measurement above and beyond what you can do using just the gravitational waves and just the redshift of the counterpart alone. Okay, so I'm running out of time, but I'm going to just briefly mention what we're thinking about in terms of how to improve, how we actually go about and look for these things using instrumentation. Okay, so as I've sort of referred to throughout this talk, Kilonovae are hard to find, and so I think I like this plot to explain that. So again, on the y-axis here is brightness, and it's in the funky, magnitude units that astronomers love. And so in black here are a variety of type of supernovae, the various stars, and you'll notice that in general, they're a magnitude or two brighter than 170817, which is down here. So 170817 peaked at something like -16 or so in these units, and so they're up to factor of 10 or more, can be up to a factor of 10 or more, dimmer than supernovae. The other thing that you'll notice is that supernovae are relatively slowly fading, and so it's not hard to see them because you can observe them and then wait a couple of weeks and then observe them again, and you expect them to still be there. 170817, on the other hand, kind of fell off a cliff and was gone within a handful of nights. And so the point is that these Kilonovae, they're intrinsically faint and they fade quickly. And so they are basically exactly the opposite of the kind of thing you want to try to observe if you want to find a lot of these things. The other thing that I wouldn't say is necessarily an observational challenge, but does make them interesting. In the sort of movie thing, I showed that we went from a blue to red, over the course of just a few nights. And so they are remarkable relative to most other astronomical transients for the amount that they redden over time. And so this is a difference between two of the colors, and it rapidly goes from blue and within a couple of nights to something very red. And so this is another way that they're different from other transients, which redden potentially much more slowly. And it may also inform the kind of instrumental choices we make in particular. Okay, so to give you a quick rundown of sort of what the state of optical time domain astronomy is, which is really dangerous, but maybe this is my own biased perspective. In general, you have a lot of these, a lot of surveys out there which have various fields of view and various cadences. And so a few of the famous ones at least. So LSST or VRO is a 10 square degree imager, 10 square degrees or so. That'll be, imaging the sky down from Chile, starting in a couple of years. Pan-STARRS is a 7-degree imager that's on Haleakala out in Hawaii. ZTF, which I've referred to a handful of times, is a 50 square degree imager on the 1.2 meter at Palomar. And so basically it turns out there's a lot of these surveys out there that they have various fields of view, various cadences, various apertures, and therefore sensitive to different, let's say, intrinsic brightnesses. But in general, a lot of these exist. They put out sort of, alerts about the transients they see. And so it becomes a game much more about how do I efficiently sort of parse through this alerts and follow them up to identify, for example, in my case, counterparts to short GRBs or Kilonovae or what have you. And so in general, to figure out which of these alerts should I care about, there's kind of two broad ways you do this. One is you identify the transients photometrically using one of these surveys, and then you get a spectrum, right? So I get a spectrum to determine, do I have a supernova? Do I have a cataclysmic variable? Do I have a kilonova? What have you? And this is, let's say, one of the most common ways that this sort of process works. The other is photometric detection, and then followed up by multi-band time series, i.e. I get multiple colors of my particular transient. This is going to be the way that predominantly people are doing LSST or VRO observations, because LSST is a survey instrument on an 8-meter class telescope, which means the 2-meter I have at Kitt Peak is not going to be particularly useful for following up LSST transients. And so this is, kind of a mix of machine learning and kind of model fitting that people are predominantly planning for LSST. And so if I was to, make a super cartoon for the observational landscape, basically you have your transient generator, i.e. your optical system. You either get follow-up using photometric facilities, getting just more images, or you go and get spectra with your spectroscopic classification facilities. And in some way you identify, through this, oh yeah, I have an object that I'm super interested in. And then you go and get deep characterization on maybe large aperture telescopes with high resolution spectrographs, that kind of thing. And so I'm going to concentrate just for a second on the spectroscopic classification problem that we've been thinking about. It turns out that we have way more photometric alert facilities than we have the ability to spectroscopically classify things. In 2019, there were almost 20,000 supernovae, CVs, potentially kilonovae, things like that, identified by various surveys. But some very, very, very small fraction were actually spectroscopically confirmed. This is a problem because while perhaps if I have a supernova, maybe I can convince myself it is indeed a supernova based on the long light curve. For my kilonova that I might just have a couple, 2 or 3 points for, I don't think that's not enough to say either way, really. And so the solution that we've been working with, we call the SED machine. And so we have a prototype on the Palomar 1.6 meter, which is, and so the idea of this thing is it's a very low resolution spectrograph. And so it's unlike kind of typical spectrographs where you have a slit, pass light through the slit and disperse it. We have a lenslet array such that we get a series of little spectra throughout the image we take. And so this is an image of Saturn. And so each of these little dashes here is a spectrum. And so there's some downsides. So you get, as I said, it's very low resolution, or something like 100. And you have these sort of nearly overlapping spectra all throughout your image. And so data reduction is kind of a challenge, but that's, at this point, it's mostly a solved problem. And so the thing that's cool is this low resolution spectrograph on the Palomar 1.6 meter is doing 50% of all classifications on the transient name server, which is sort of our field's, announcement thing, announcement database. And so, and it's been doing, 10 to 20 targets per night to identify, to do classification. And so this is a plot where in pink is the SED machine, and then blue is DBSP, which is a relatively higher resolution spectrograph on the Palomar 5 meter. And it's ours small, but it's enough to accurately identify this as a type 1a supernova, for example. And so we're, to get ready for 04, we're planning on building a second version of this, but let's say better. So as I mentioned, the current one is on the 1.6 meter. We're going to move it to a 2.1 meter. So we'll gain, let's say, sensitivity in that way. It's a robotic it's a robotic telescope we've been using for a few years to do high cadence photometric follow-up. Broadly, the plan is to optimize the quantum efficiency of the detector, improve how we did the throughput or the optics that the lenslet array to improve throughput. And so we'll be building another one of these hopefully this calendar year to put a second working version on this 2.1 meter. And so the idea is that we should be able to go down to something like 19th magnitude with this system, again, doing 10 to 20 objects per night, but basically fainter than we're able to do with the SED machine, which is important because, as I mentioned at the beginning, Kilonovae are intrinsically faint. So you need a spectrograph that can do faint objects quickly. Okay, and so I'm going to close here. I hope I didn't take too much time, but I will just say big thank you for inviting me, and I hope that it was okay. Thanks.
Thank you. That was great. I got a question first, if you don't mind. Other than the 1987 supernova that saw the light and the neutrinos, has any other event ever correlated the neutrino observation with any neutrino experiment with anything else yet?
We have a claimed TDE counterpart that we just published in Nature Astronomy. So we've been doing dedicated ice cube follow-up with ZTF for the last few years. So again, just like the gravitational wave in the GRB case, ice cubes putting out sky maps, and their localizations are actually much better. So gravitational waves cover 1,000 square degrees, GRBs are kind of like hundreds, neutrinos are like 1. And so it's not too hard to do with ZTF. And in our case, we have an event where we have a tidal disruption event that was going off at a let's say on a similar time scale, and statistically, it's actually surprisingly unlikely to have that happen. We have a few more candidates that we've put out, but that's the big one that we've just recently published. Yeah, so it's not a lot. The sample's not a lot, but I think it's becoming more of a thing to do. I know of a bunch of programs now where people are doing optical follow-up of IceCube. And it seems like people are figuring out how to, let's say, parse the alert stream for these things. Yeah.
Okay, I didn't know about that. I'll have to look it up. Yeah. You said it's an IceCube preprint or a publication?
Yeah, it was published in Nature Astronomy last week, something like that.
Oh, yep. That should be easy to find. Okay.
Yep.
Other questions?
I have a question.
Go ahead.
I know you're not very interested in exoplanets, but do you find exoplanet science very interesting?
So if I was to give a second colloquium, it would be about high cadence photometric follow-up of white dwarf binaries. And so in that case, the problem there is actually super, super similar to what goes on in the exoplanet community. So the idea, so in exoplanets, right, you have some usually high cadence photometric imager, and that's looking for predominantly eclipsing systems, and then you get follow-up photometry, high cadence photometry to confirm that indeed you have an eclipsing system, and then maybe you use a really high resolution spectrograph to get a spectrum of it. In my world, I do something very similar where I take ZTF, I have long baseline photometry of white dwarfs, and I period search them to look for potentially short timescale variable objects that are potentially eclipsing. I get photometric follow-up to confirm, this kind of eclipsing event, and then I, get in my case, I get phase resolve spectroscopy to get RVs. And so, yes, I'm a big fan of the exoplanet people. I definitely steal techniques from them, especially with regards to the period finding and how they find periodic behavior in time series all the time. So I think it's, I don't know if that answered your question, but that's, yeah, I steal their, their work to make my work happen. Yeah.
I have another question. What is your favorite exoplanet system?
So I just gave my big data astro class, what is it, Kepler, one of the Kepler systems that has like 8 or 9 planets, and I just asked them to basically period find the light curve and identify all of the transits or whatever. So that one's currently my favorite one. I'll have to look up whichever one that was, but yeah, it was a pretty gnarly problem. So I was excited to give it to them.
I mean, one of my top 5 favorites is probably the TRAPPIST-1 system.
Yeah,
sure. But I also like circumbinary ones as well, like Kepler 16 that has like, I think it has like 3 planets and 2 suns. I'm not really 100% sure, but yeah.
No, it's cool stuff.
Okay, one more thing. How did you feel when the first circumbinary planet was detected?
So I'd say as a person who's not in the field, I think the thing that remains, I find it a truly a technical marvel, right? I mean, like for example, if you take TESS, right? You have it's a space-based imager, so it's easier than doing it on the ground, but their photometry is at literally at 0.01%, right? I spent my PhD trying to make such that LSST will do 1% photometry, and they're literally orders of magnitude already ahead of this 8-meter class telescope I spent a bunch of time trying to figure out how to calibrate. And so I think the technical marvel that goes into the predominantly exoplanet searches is really what I think is truly amazing. It's sort of where I'm at.
Okay, I had a question which you might have covered this some in slide 42, but I was curious when you were talking initially about the GRB, where you said you had to wait several hours until it was dark and chilly to see it. Yeah. That just made me curious about what is the coverage? So you mentioned both hemispheres, but yeah, I'm just curious, why did you have to wait for the sun to set in Chile? Why couldn't there have been some other place to observe this? Is it related to worldwide coverage, or?
Yeah, so so if it was to happen now again, there's the South African Observatory, especially with SALT, which is a large aperture telescope, now has very much a dedicated program to this. But I think it caught people just a little off guard, to be honest, especially because you want well, different people debate this, but you would like a sensitive wide field imager that does transient detection on a nightly basis wherever you are. And so that meant that you would have wanted one, for example, in South Africa at SAAO, but they just weren't ready for that. Whereas now with, anyways, they're better tooled up nowadays. Chile is just the place that does have, let's say, most of these systems. 170817 was in the south, which meant that you wanted to have a imager or spectrograph in the south to do this, and so there's your hemisphere coverage. But the temporal coverage, of course, matters too. I mean, there's only a handful of, let's say, real sites, around the world, right? And we sort of can name them as we go through the time zones. And so we jumped from South Africa, which during 2002 at that time just wasn't quite there, and then to Chile, where people were quite ready to do this. And so again, during 2004, things would be different, like this next observing run. But yeah, back then it wasn't quite the same.
And then, do you know, are there observatories in Australia or India in case, all right.
That's right. And so, for example, Sliding Springs in Australia, they're also very tooled up for radio searches. So the Australians have been doing all sorts of radio searches during 2003, especially in India and in Tibet, for example. So there's a part of collaboration I'm in, has a instrument. In India, there's a telescope in Tibet that's nearly dedicated to this during the gravitational wave runs. And so, yeah, basically there are some pockets through time zones that are less good, just in terms of aperture and seeing. So some of these sites are more or less good. Some of the telescopes are more or less large, but I think nowadays there's enough sort of 1 to 2 meter systems that people are sort of coordinating on that it's less of an issue than it was a few years ago, let's say.
Thanks.
Well, any other questions? All right, it looks like none, and it is after 3 o'clock, so let's end it here. Thanks for a very nice presentation again, and see you all again for the next talk in our seminar series.
Thanks for having me. It's really nice.